Hi students, ఈరోజు మన వీడియోలో we are going to see the extension of the last cover topics. That is, we have seen in the last class what is electric potential, and we have seen expression for the electric potential at a point due to a dipole. So later topics are also important, but anyway, as you see, now this particular topic is very important in the from the point of view of competitive exams like JEE, NEET and all. So let us concentrate on this particular topic and try to understand the potential energy of a dipole in an external field. Fine. So basically, the basic is potential energy. Whatever the work that is done, it will be saved in the form of potential energy, right? So here let us see what is the potential energy of a dipole in an external electric field. So as you observe here, as you see, so if there is a uniform electric field, actually from here to here, from left to right, as mentioned by the arrows, as you see here, so that when I say uniform, I mean the intensity or strength of the electric field is same at every point. So therefore, this is the electric field, fine, as given by the arrows here. So this is the electric field acting in this direction. So therefore, whenever a dipole means yesterday we have seen two polarities, a positive polarity and a negative polarity, separated by a distance of 2a units, and in between exactly at the center, actually there will be a dipole moment vector p bar acting from minus q to plus q. So if a dipole is kept at an angle in an external field, what exactly is the potential energy? So I told you that work done will be saved in the form of potential energy. It is not potential energy, but anyway, work done will be saved in the form of potential energy. Now let us try to understand whenever a dipole, so here as shown in the figure, a dipole is kept in a uniform external field, right? So this dipole is having charges, one is plus q and see the second charge is minus q. Now as you see, observe here, it is making an angle theta with the direction of the field. So therefore, what is obviously this one? Now as you observe here, because from total distance from positive charge to negative charge is 2a, half of the distance becomes a, and obviously if this is a and this is cos theta, this becomes a cos theta and this is minus a cos theta. Fine. So it is shown that the direction of electric field is from left to right. Now when a dipole is kept at an angle theta to this electric field, what exactly is the potential energy? So first we understand one thing, one point. So whenever a dipole is kept, in the last chapter itself, we have seen that whenever in a uniform electric field, a dipole experiences as such a zero net force. What is that zero net force? Because a force of magnitude E into Q, as you see here, whenever a charge Q is kept in an electric field E bar, it will be experienced by a force F is equal to QE. Right? Since it is a dipole, two forces will be acting, but these two forces, because one is positive charge and other is negative charge, two forces which are opposite in magnitude, which are equal in magnitude, but opposite in direction. So they will be acting at the ends of the dipole. So when you observe that, when you see a force, for example, a force F is equal to QE is acting in this direction and F is equal to minus QE is acting in the opposite direction, because the magnitude is same, their net force is zero. Though the net force is zero, that means the resultant force, that means when you consider the free body diagram, the resultant force is zero. No, absolutely there will not be any net force on the dipole. But what will exist? What will exist is, there will be a force, you see, it experiences a torque. A twisting moment will be there because of these two forces, whereas one is positive force, that is of magnitude Q into E bar, another one is Q into minus Q into E bar. When these two forces parallelly they are acting at the ends of the dipole, they try to rotate the dipole. So therefore, this is the bending moment or twisting moment. That's what we call torque. So torque is it is the bending moment, right? Or it is a twisting moment, right? So therefore, the torque magnitude is given by P bar cross E bar. That's what we have seen. If P bar is a dipole moment vector and E bar is the magnitude of the electric field, P bar cross E bar, it is going to be again vector. So torque is a vector. Torque is the analogy, see, for the force See, that means in linear motion, so just as how force will be there in the angular analogy of the force in the angular motion is torque. So therefore, torque is obtained as P bar cross E bar. That's what we have seen. So though there is no net force is zero, but because these two forces are acting, you see, they are trying to rotate. They are trying to rotate the dipole in this direction. So here particularly if they are acting like this, so they will be acting in clockwise direction to rotate the dipole. So therefore the magnitude of the torque is given as P bar cross E bar. Now once you know that torque, you see here, it will try to rotate. It will try to rotate what? The particular dipole, right? So therefore, P bar cross E bar will become zero only when, because we know cross product becomes zero when the angle between them is obviously parallel. That is, P bar is parallel. Unless and until P bar is parallel to E bar, this torque cannot be zero. So dipole moment, if it is parallel to the electric field, then sin theta component of P bar cross E bar, it becomes zero, and as such, the torque also becomes zero. So therefore now, so try to understand that this torque or twisting moment will be acting, say for example, in clockwise direction. That is what you see here. Now this is actually the torque because of the two forces, right? Now therefore, in order to balance or to make it into the equilibrium, an external torque must be applied in such a manner that it just neutralizes the torque. So whenever you find T external, that means what? To this torque, in an anti-direction, one more torque must be applied to get back the dipole into the previous position. So therefore, so whatever then that is how the work is going to be done. So work done in that case, which is work will be done by the external torque in rotating the dipole back, because of the pair of forces, that is, one is acting at the positive charge of magnitude Q into E bar, and another force that is acting at the other end of the dipole minus Q into E bar. These two are equal in magnitude, but they are in opposite in direction. So therefore net force is zero, but these two forces which are acting simultaneously, they result in a torque or twisting moment. They try to rotate the dipole. So in order to bring the dipole back to the original position, you need to apply some external torque which neutralize the effect of this torque. So therefore work will be done by the external torque. So therefore work is nothing but force. I told you work is equal to force into displacement. The angular analogy of force is torque here multiplied by distance. So here it is not linear distance, this is angular displacement, so which is d theta. So tau, which is a function of theta, multiplied by d theta within the limits theta naught to theta 1. So for example, now if it is bringing, now you see here this external torque now is again bringing it back from theta naught to theta 1. So the limits of theta must be taken as theta naught to theta 1. But we know that equal amount of torque must be applied to neutralize. So P bar cross E bar only, which is nothing but P sin theta only. So P sin theta d theta only will be the external torque, so which neutralizes the original torque. So therefore work will be done by the external torque to neutralize the effect of the bending, that is twisting moment of this torque or couple of forces. Now you see here, so P sin theta d theta. Now because P is dipole moment vector, P is dipole moment and E is the magnitude of the field, integral of sin theta is nothing but minus cos theta. So therefore it is simply cos theta naught minus theta cos theta 1 rather than cos theta 1 minus cos theta naught, because it is going to be minus cos theta. So finally we got work done is P into cos theta naught minus cos theta 1. As I told you in the beginning, so the potential energy is nothing but the work, whatever the work that is done in the system, that will be saved as potential energy. So therefore we can say that this work stored is in the form of potential energy, and as such, no, the expression for potential energy is capital U, so which is going to be again a function of theta. So U of theta is equal to P into, as you see here, it is cos theta naught minus theta 1. So the angles that we can decide, say for example, if that external torque is rotating from pi by 2 radians to theta, so you can keep pi by 2 here, cos pi by 2, cos 90. So obviously it is 0. So therefore it is P into minus cos theta. Now you see here, now P into cos 1, cos it is pi by 2, cos 90. Cos 90 is what? How much? Yeah, it is 0. So 0 minus cos theta, fine. So you can say it is minus P bar dot E bar, leda minus P cos theta. So this is how we can derive an expression for potential energy that is of the dipole. So potential energy of a dipole in an external field is nothing but minus P bar dot E bar or minus PE cos theta. So that is how we can prove, friends. Fine. Now next let us look at the extension. What is the next thing? So so as you see here, it is minus PE cos theta. So you can apply in the corresponding sums wherever you get sums like this. Now let us understand. In order to go for capacitance, we need to understand some of the basics. The basics are electrostatics of conductors, because no normally before going for capacitance or capacitor, as you see as you know, capacitor is one of the passive devices like inductor and that is inductor and what is the other one, resistance, capacitance and inductance, right? So therefore capacitance, inductance and resistance, right? So capacitor is another passive device like inductor. So we are going to study capacitor in detail, particularly parallel plate capacitor. Fine. So anyway, let us go directly to what is called capacitance and fine. Now, so wherever we require, we come back. So time being, let us go to the capacitor part. Now, now you see here, before going for capacitance, it's important to look at the dielectrics and polarization, because normally a capacitor is filled with a dielectric or an insulator in between the plates of the capacitor. So parallel plate capacitor will normally build with will be built. See what will be there as a medium in between the plates. So a dielectric. Fine. So we need to know about dielectric and polarization. So what is polarization and what is dielectric? Let us understand in detail what is dielectric and what is meant by polarization. So in simple terms, polarization is the orientation of electric field vector. So whatever the direction of the electric field, that we are going to study as the polarization, right? So you may ask, sir, what is the need of studying all these things? Particularly, let me tell you one thing, one fact here. Polarization is very much applicable for particularly, so whenever you are tuning your, say for example, your TV receiver to a particular channel, so normally you know that you must be knowing that the frequency starting from the satellite, transponder and then frequency, not only the frequency band and then data rate and of course finally polarization, whether it is going to be circular polarization or electrical see, it is going to be elliptical, left circular or right circular. So different polarizations are there. So kabatti meer నేర్చుకోవాలమ్మ కంపల్సరీగా what is exactly meant by polarization. Fine. So kabatti enduku application ekkada untundi ante I am telling you, if you want to see if you want to see a favorite channel in the newly installed, say for example Tata Sky or Dish TV connection, a satellite TV connection, what you need to do, you need to just give inputs like polarization. First, you need to give starting from satellite, transponder, and then frequency, band, and then finally polarization. Fine. So, kabatti oka particular polarization meeda you are going to get your channel kada. Kabatti you need to understand dielectrics and polarization in detail. As you see here, so let me just give you a brief on this polarization part and dielectrics. So as you know that dielectrics are non-conducting substances, they are actually insulators, right? Unlike metals, they are not good conductors of electricity. Now in contrast to conductors, they have negligible number of charge carriers. They have no charge carriers, and that is how a dielectric will be constituted. Fine. A dielectric will be constructed or constituted, right? Now if you see, now the difference between a conductor and a dielectric, now you see in the figure itself you can easily identify. Yeah, for a given conductor, if you see the lemma, if for a given conductor, as you see the direction of electric field, and within the conductor, what is actually E naught, direction of E naught, and what is the direction of E in, and what is the sum of external electric field and inside the electric field. Let us understand here. Now, now as you see here, now taking a conductor, particularly, as you see the difference, now, particularly when you look at the electric field inside, this is the external electric field, outside electric field expressed by the symbol E naught. The subscript 0 indicates that it is external electric field. Now as you see here, now the only difference that you observe here is whatever the electric field developed inside the conductor that is equal in magnitude to that of the external electric field. So these two are in opposite in magnitude and opposite in direction and equal in magnitude. They compensate, they cancel each other, resulting in a zero electric field inside the conductor. But for a dielectric, it is not the case. Whereas external electric field is larger in magnitude. So when compared to the electric field produced inside the conductor, that is dielectric, so with the magnitude of only half, approximately only this much magnitude will be there for inside electric field. And as a result, what you can have, you see the sum of the external electric field and inside electric field is not going to be zero. That is the only difference that you can very much observe freely here. Here you see two arrow marks, two arrows in opposite direction, equal magnitude. So therefore, E naught stands for external electric field or outside, whereas E in is the inside electric field. So in terms of charge carriers also it is given. So therefore, E naught plus En is going to be 0 in the case of conductor, but E naught plus En is not going to be 0 in the case of a dielectric, right? That is the difference you observe here. So unlike in a conductor, however, you see here, unlike in a conductor, however, the opposing field is so induced doesn't exactly cancel the. So therefore, whatever the induced field inside, that will not cancel the external electric field because its magnitude is only half or even less than that. So therefore, resulting magma electric field is not going to be 0. That's what you understand now. Now, to understand you understand, right, why the exact effector. So we need to look at the charge distribution of a dielectric. So this effect we need to understand in detail. So unless and until you go to the micro level of the dielectric, you cannot understand it. So therefore you need to go to micro level of dielectric. So dielectrics, okay. So therefore we need to look at the charge distribution of a dielectric. Then only you can understand the effect, right? So as you see here, now basically we have two things here, polar molecule and non-polar molecules. So some of exam of the you see here. Now when you go to the molecular level, fine. The molecular level of it may see a molecular level if you go particularly for a dielectric, that then only you can understand the typical behavior why the induced electric field is not equal in magnitude to that of the external electric field. So it can cancel, right? So that is not happening in the case of a dielectric. So the only option to understand that you need to go to molecular level. So when you look at the molecular level, see basically for any substance molecules of two types. One is polar molecule and non-polar. Fine. Now as you see here, now the centers of positive and negative charges coincide. Particularly in a non-polar molecule, the centers will, you see here, the centers of positive charge and negative charge. Now the centers will coincide in the case of non-polar molecule, but for polar molecules, centers do not coincide. That is what you observe here. Now here you see here, the centers are going to coincide. Here also the centers are, some of the examples for non-polar molecules are hydrogen and carbon dioxide. Okay, but for polar molecules, you see here, HCl and HCl and water molecule, they don't have the centers aligning in the same line. So therefore, their centers are not going to coincide. So in the case of a non-polar molecule, the centers do coincide, but in the case of non-polar molecule, that is polar molecule, they'll coincide, right? So they do not coincide, and here they'll coincide, right? Now, if that is the case, what happens? Now you see here, particularly in an external, you see here for both polar as well as non-polar molecules. As you see for non-polar molecules, two cases, one external electric field is 0 and when external electric field is not 0. And for polar molecules also when external electric field is 0 and when there is no, see, external electric field is totally 0 here, but external electric field is not 0 here. For both the cases, like for non-polar as well as polar molecules, for these two things of E is equal to 0 and E is not equal to 0, we need to look at the scenario. Now, when you see the scenario as you here, for I told you non-polar molecules, the centers do coincide. So therefore, this is how when there is no external electric field, E is equal to 0. Fine. Normally they are actually coinciding. What happens when electric field, external electric field is 0 and if it is not 0? That means when there is some electric field, no, they reorient themselves. As you see here, a minus and plus sign, instead of coming in the same line, they aligned in this manner. As you see here, now Now, what is meant by polarization? I told you that it is the orientation of the electric field. So we need to look at the electric field orientation and how the particular molecules of a substance, when you go to the molecular picture or molecular level of a dielectric, so how they are getting oriented. That's what we need to see. Fine. Now, in the case of non-polar molecule, actually there will be an induced dipole moment. The dielectric is said to be polarized by the external field. That's what. So when there is when the external electric field is not zero, that means when there is some external electric field, what is happening is now there is an induced dipole moment. As such, here dipole moment I told you Q into 2a. So what is dipole moment? Charge multiplied by distance. Here actually they are displaced mutually. So there is a net dipole moment you observe here because of the distance between what you see these charges, right? Negative and positive charge. So therefore, non-polar molecule will have an induced dipole moment when there is some. Fine. So when there is when there is an external electric field, they are actually polarized. So this is what is polarization. But when coming to the even for polar molecules also, as you see here, right? Now, do you observe now here it is because of the electric field, they are polarized. That means the centers are realigned. Okay, that is what induced dipole moment. Next one. Fine. In the case of next one, you see this is for a polar molecule where electric field is 0 and electric field is not 0. What you exactly you can observe is polar molecules develops a net dipole moment in an external field, but for a different reason. So in the absence of any external field, the different permanent dipoles are oriented randomly. Now you see that is that there is a difference of reason. Now in the case of see when the net electric field is 0, so they orient themselves in a random manner, as that's what mentioned here. So oriented randomly due to thermal agitation. It is only due to thermal agitation, but when there is an electric field, again there will be an induced dipole moment. So as you see here in this picture, so when there is external electric field is 0, only it is not because of any other reason, but only because of the that's what thermal agitation of the molecules. Therefore, just this alignment, whatever the alignment you see here, this is because of thermal agitation. But when there is some external electric field, as you see here, now there is again a net dipole moment. So whatever the case may be, this is how net dipole moment is induced. Fine. So whether that's what, when an external field is applied, the individual dipole moments tend to align with the field when summed overall the molecules. That's what. So therefore, when you sum all the dipole moments of the all molecules, it is going to be your net dipole moment, right? That's what you observe here. So that is how a dielectric is said to be polarized. Fine. So the extent of polarization depends on the relative strength of, you see the field tending to the relative strength of the two mutually opposite factors, right? So that is how you can observe that. Now, coming to, fine. So now we are going to define the net dipole moment in the Preci. In either case, that is whether it is non-polar or polar molecule, whether a polar or dielectric develops a net dipole moment in the presence of external field. Now, what is the magnitude of that dipole moment? You express in terms of Xi, a parameter. So you see here. Now, so we call it as susceptibility. So we are going to express the net dipole moment, and we are going to get a relation for this net dipole moment as a function of electric field, but with the characteristic, a constant of the medium, this not only epsilon naught, permittivity of the medium, but one more characteristic of the medium called Xi. So therefore, it is called susceptibility. So this net dipole moment is related to electric field by two characteristics. One is permittivity as well as susceptibility. So P is equal to epsilon naught Xi into E. This symbol is for particularly Xi, Xi. So therefore, the symbol E, the so-called suffix, so that is net dipole moment is equal to epsilon naught Xi, and Xi is a constant characteristics of the dielectric. Okay, this is called electric susceptibility. Right? So kabatti we understand what is dielectric and where the dielectrics are used. So this is how we can talk about the polarization, right? Next, if that is the case, now you just see here a uniformly polarized dielectric amounts to induce surface charge density but no volume charge density. So that is what is happening at the ends, as you see here, because at the ends you find there is a net surface charge density, but there is no volume charge density. So as you see, uniformly polarized dielectric amounts to induced surface charge, because the corners of the, as you see, if this is a dielectric surface, at the ends you find negative and positive charge. So opposite charges are in between. So therefore, obviously you'll have surface charge density sigma, but there is no volume charge density rho, because we have charges only forming at these surfaces. So here there is no question of volume. So that is how we can define something called surface charge density sigma here. Fine. Next. Now let us look at capacitors and capacitance. Now, so once you understand the term dielectric or insulator, so whenever two conductors, you see here, a system of two conductors are separated by a dielectric or insulator, now the entire system is going to be called as a capacitor. Now what is exactly capacitor? Capacitance, if I have to define orally, it is capacitance is the number of simultaneous, say for anything, subscribers or something. Here also number of simultaneous charges. So what is a system? What is that capacitor system is all about? Kabatti, whenever you have two conductors, as you see, two conductors separated by something called dielectric, fine. So that is what is called a dielectric or insulator. So therefore, as you see, if a total positive charge is there on one side of the conductor, this one, and the other side for conductor 2, there will be equal amount of opposite charge will be induced. So therefore, if it is Q, it is going to be minus Q, and if it is at a potential V1, it is going to be at a potential V2. Fine. Now that is what a capacitor is, a system of two conductors separated by an insulator, and conductors have charges say Q1 and Q2, and potentials being V1 and V2. Now, you know, anyway, potential difference going to be V1 minus V2, and so that's what we are going to explain, right? So this is a setup for a capacitor, and capacitor basically, what is the basic use of capacitor? To store the energy, right? And as you know that passive devices are conductor and capacitor. So therefore, in AC circuits and all, we are going to learn that, see, capacitor acts as a passive device, and it opposes DC, whereas inductor opposes AC, capacitor opposes DC, and allows AC, alternating current. So whereas in the positive cycle of the alternating current, it charges, and in the negative cycle of the alternating current, it discharges. That's how a capacitor works here. Now, so given the potential difference, and given the amount of the charge on the each plate, the capacitor is defined, capacitance of this capacitor is defined as a ratio of charge to voltage. So C is equal to Q by V. Then what is C? C is the capacitance of the capacitor. So therefore, Q being the charge on each plate, and ignoring the sign or this one, and V being the voltage potential difference, and C capacitance is nothing but it is a ratio of charge to voltage. Fine. That's what. Now this is what electric field in the region between the conductors is proportional to charge Q. You know that because electric field is equal to 1 by 4 pi epsilon naught Q by R square. So therefore, if the charge on the capacitor say doubled, electric field also gets doubled. So this is what we can say. Now, if the charge is doubled, electric field gets doubled. Now potential, if we know we have the relation between electric field and potential. So therefore, that's what yesterday we have seen. The electric field and potential. Electric field, what is negative gradient of potential? It is simply E, kada? That's what we have seen. Fine. So therefore, what is the basic definition of capacitance? Mathematically, capacitance is defined as the ratio of charge to voltage. Now, fine. So, now there is a point, important point to note here, that what is the maximum electric field that a dielectric can sustain? If you see that the maximum electric field that a dielectric medium can withstand without breaking is somewhere around 3 into 10 power 6 volt per meter. So if you apply 3 million volt per meter, so 3 million volt per meter is the maximum electric field that a dielectric can sustain without breaking, and once it receives approximately 3 million volt per meter, like the dielectric is going to break down, right? So that is what we call it as dielectric strength for a given medium. Fine, dielectric medium. Now, now let us look at one of the basic capacitors because its expression is important. Nana. From short answer questions, you can expect one SAQ from this particular concept. Section of the capacitor, parallel plate capacitor, right? So how to derive the expression for the capacitance of a parallel plate capacitor? Simple. Look at the construction of the parallel plate capacitor. As the name suggests, as the name implies, that we'll have two parallel plates, plate 1 and plate 2. And you consider three regions here, a region above the plate 1 and you consider the region below the plate 2, and of course we consider the region in between the plates. So this is both are having the same area, plates both 1 and 2, and there exists, as you see here, there exists electric field from positive charge to negative charge. Since there is a positive charge on the plate 1 and equal amount of negative charge on the plate 2, they are separated by a medium here. Now therefore, there exists an electric field from positive charge C, from all positive charge to from negative charge. So the direction of the field is obviously from positive charge to negative charge. So this is how E is oriented in this direction. Let the distance between the two plates that we are taking be d, small d. So for the three regions of 1, 2 and 3, we are going to calculate the net electric field, and then obviously we are going to get expression for capacitance of a parallel plate capacitor. Fine. Now as you see here, d, small d is the distance between the plates. We are going to get an expression that C is equal to epsilon naught A by d, or simply this is the expression we are going to get. Capacitance is equal to epsilon naught times of area of the plates by distance between the plates. C is equal to epsilon naught A by d is the simplest expression that gives us the magnitude of capacitance for a parallel plate capacitor of two plates having an area of cross section of U units or a meter square and distance between them being small d units. Okay, to go for it, we need to just, you see, we are going to relate, we know, because V is equal to ED. So how we are going to get is very simple. As I told you, you need to take three regions, region 1, region 2 and region 3. So for outer region, as you see here, for outer region, this is the outer region. So because we know that, what is electric field due to a surface charge density, because I told you in the previous classes that we have basically three types of charge densities: linear charge density, surface charge density and volume charge density. Now consider that these two are plates with area A. So obviously this is nothing but a surface. Plate is nothing but its surface. So charge on the plate is nothing but it is basically surface charge with density sigma. So therefore, sigma, if sigma is the density of each surface, that is plate 1 and plate 2, then we know the expression for electric field due to this surface charge. Because we have got three expressions for electric field due to a line charge distribution, surface charge and volume charge. So this is sigma. Sigma is the surface charge density. So electric field due to one charge density, that is sigma by 2 epsilon naught. This is the basic expression due to a single surface, that is with surface charge density sigma. And if that is the case, when you consider region 1, because of positive charge, obviously this is going to be the total electric field. And due to a negative charge, it is going to be other one, that is minus of sigma by 2 epsilon naught. So these two get added here. One is because of positive charge and one is because of negative charge. So therefore, obviously these two will cancel each other's magnitude. So in the region 1, the net electric field is 0. Fine. Why? Because when you superimpose, so this is, as you see here, when you superimpose, the total electric field becomes 0. That is electric field due to sheet 1 as well as sheet 2 must be added. So that is how it resulting in, is going to result a 0 electric field. Now for the next case, for the region 2, that is below the plate 2, also is the same. So only the direction will be changing. Sigma by 2 epsilon naught and minus sigma by 2 epsilon naught both get added to give a 0 electric field beneath the second plate. So in between these two plates, you need to the only difference is because one field will be in, see, both the fields get added because one field is due to a negative charge. So only in the region between the plates, these two fields get added. But in other two cases, they are going to cancel each other's magnitude. So finally, in the region between the plates, electric field must be summed. So because of positive charge distribution and negative charge distribution, it is going to be sigma by 2 epsilon naught plus sigma by 2 epsilon naught, which is nothing but sigma by epsilon naught. And sigma, for that matter, because it is charge density and that is surface charge density, so it is, we can replace it by Q by A, charge per area, because the basic definition of charge density lies as charge per area. So Q by epsilon naught A becomes our electric field. And finally, in order to derive, so this one, because V is going to be ED, the relation between electric potential, as I told you, electric potential, electric field is a negative gradient of potential. So V is equal to ED. So because you see here, this is 1 by, now just now we got the total expression for electric field is Q by epsilon naught A. So Q by epsilon naught A multiplied with D. So that is gives you what is V. So substituting the value of Q as well as V, V is just now obtained as, you see here, whereas Q will be in the numerator only, but in the denominator, V will have QD by epsilon naught A. Q and Q will get cancelled, finally giving you a value of epsilon naught A by D. This is what is called capacitance of a parallel plate capacitor. Fine. Taking an approximate values for C, for a special case of distance between plates as 1 millimeter and area of 1 meter square, and you are approximately going to get the capacitance value as 8.854 into 10 power minus 9 farad. So farad is a nominal normal unit. So still lower units like microfarad and picofarad are there. But anyway, 8.85 into 10 power minus 9 for a special case of A is equal to 1 meter square. That is, area of the plates is 1 meter square and distance between plates is 1 millimeter. By substituting the value of epsilon naught, this is your epsilon naught value of 8.85 into 10 power minus 12 into A value is 1 meter square. By D is, now converting into meter, it is 10 power minus 3. So you are going to get it is 10 power minus 9. So that is how you can say 1 farad. So to define 1 farad, it is very simple. Now basically, in order for capacitance to be 1 farad, you need to take a charge of 1 coulomb and you need to take a potential of 1 volt. So 1 coulomb per 1 volt can be taken as 1 farad, right? So therefore 1 coulomb per 1 volt is taken as 1 farad, right? So this is how we can express the derivation for the capacitance of a parallel plate capacitor. Now, right? Now, what happens exactly if a dielectric is kept in the exactly in the, see, as a medium between the two plates? Effect of a dielectric on capacitance. So it is basically very important from the from the competitive exam point of view. So whenever a dielectric is kept exactly in between the plates of a parallel plate capacitor, what happens to the total? What is the total effect, right? So we are going to see that. Sorry. Yeah. Now, so this is, we are going to get dielectric constant or see relative permittivity or dielectric constant. So what we are going to see, what happens exactly when you keep a dielectric, fine. Now this is what the final effect, just let me explain. The final effect is going to be, now capacitance, as you see, it is becoming K times. If the dielectric constant, or if you see the relative permittivity, if the dielectric constant of the medium is K, then capacitance will be increased by K times. Capacitance with dielectric between the plates is, it will be increased, right? So that is how it happens. Now for vacuum, K is equal to 1, because you know where epsilon R, relative permittivity, and K is equal to 1. So now your epsilon becomes epsilon naught. So therefore K is nothing but epsilon by epsilon naught. I told you it is nothing but epsilon R. So therefore relative permittivity itself is called dielectric constant. Fine. Because the what happens to the voltage? No, becomes, it will be reduced by a factor K and capacitance will be increased by a factor K. So whenever a dielectric of constant K is kept, so you find that the total voltage will be reduced by a factor K and the capacitance will be increased by a factor K. That's what we can see here. That is the effect of a constant. Particularly the dielectric constant of a substance is the factor, right? That is what we can see as the constant. Next one. So we can have some problems on this. Now in the next class we are going to see what is combination of capacitors, because just I'll give you overview. Just as how we have resistances connected in series and parallel, we have capacitances connected in series and capacitances connected in parallel. The only thing is, so you can now itself you can see when capacitors are in series. So that is, see, you see here, for the negative plate of the first capacitor, a positive plate of the second capacitor is brought in between, that is connected. So that is how when they are connected in series, like this, a positive charge followed by negative, again second plate's positive charge. So what happens to the net, see what happens to the net capacitance. So we are going to see, because voltage is nothing but sum of the voltages, so we can say it is nothing but Q by C1. So in the case of series combination, it is voltage that is going to be divided. So because if you rewrite voltage, it is Q by C1 and V2 is Q by C2. So therefore, we are going to get for a series combination, just like in the case of resistors, how we get parallel for them. So where 1 by R is equal to 1 by R1 plus 1 by R2, we are going to get 1 by C is equal to 1 by C1 plus 1 by C2. On the other hand, when capacitors are connected in parallel like this, so this is the parallel combination of capacitors. Now what happens to there? Now here, now the only thing is, since you see here, whereas Q1 is equal to C1V, voltage will be the same across each capacitor. So therefore, Q1 is equal to C1V, Q2 is equal to C2V. It is only that the charge only gets distributed. So therefore, we can write CV is equal to C1V plus C2V. That is, total charge is equal to sum of the individual charges. And that nothing but C is equal to C1 plus C2. So when you get C is equal to C, that's what the other result for resistances for parallel connection, for series connection, whatever you get there for series, you are going to get the same for in the case of parallel combination of capacitors. That is totally opposite. Fine. You have some problems based on this. Fine. Now we can. This is last expression, important expression to get to understand what is the energy stored, because the basic function of capacitor is to store energy. Fine. So what is the expression for energy stored in a capacitor? That's what we have to go and see in order to get the work. See, because energy is nothing but work done here. So to understand what is the total energy stored in a capacitor, as you see here. Now how to get an expression like this is the total energy or work done. Fine, whether it is half QV or half CV square or Q square by 2C. Now that's initially you need to understand one thing. For example, here as you see here, when you see wherever it is energy stored, you can get energy stored only by taking the work done. Here when see to take a positive charge from one conductor to the other conductor, work will be done externally. So that work will be carried out as, because work is equal to Q by C, Q is equal to CV, fine, or W is equal to, you see here, integral of W dash dW, so that is your Q dash by C. Fine. So therefore, as I told you, W is equal to VQ, delta W becomes V dash into delta Q dash. That's what when I apply here Q dash by C into delta Q, I get what? 1 by C as constant. Now integral of, you see here, this is nothing but integral of Q. It is Q square by 2. So Q square by 2C, and when applied between the limits 0 and Q, you are going to get Q square by 2C, or accordingly you get C when Q is replaced by CV, C square V square by 2C or half CV square. And lastly, when C is replaced by Q by V, so Q will be cancelled and it is going to be half QV. So this is the final expression for my energy stored in a capacitor, right? As I told you, capacitor is a passive device which stores energy, and just like inductor, it actually in the case of DC circuits, so it doesn't allow DC, but it allows AC to get charge and discharge. This is how the expression for energy stored in a capacitor can be carried out. Friends, ఈ వీడియో మీకు చాలా ఉపయోగపడుతుంది. So in the next video, we'll come up with some other important topic. Till then, bye.